Hello everyone. In this video, we are going to take up one example to design an FIR filter, and the filter specification is as shown. A low pass filter is to be designed with the following desired frequency response: HD of e power j omega, but in short we can call it as HD of omega is e power minus j2 omega for magnitude of omega less than pi by 4. Mind you, we have magnitude here. Okay, so and is equal to 0 for magnitude of omega in between pi by 4 to pi. There is a when I say magnitude, there is different kind of meaning is there, which I will let you know. Okay, but just take care, we have magnitude. So omega is we have magnitude there. Okay, what I need to find here is I need to determine the filter coefficient HD of n. Okay, and also I need to find h of n if the window function is rectangular window. So w of n is a window function, is a rectangular window. Okay, and the length of the rectangular window which they have given is 5. So I need to design a fifth order FIR filter with a window which is the type rectangular window. Okay, once I'm done with the designing, once I get h of n of length 5, I need to find its frequency response as well, because he has also asked find frequency response h of omega of the resulting FIR filter. So, okay, so my aim here is to, first part is I need to get HD of n. This is the desired impulse response. Okay, next part is I need to get h of n. I will let you know the relationship between h of n and HD of n. Okay, and the next thing I need to find is its frequency response h of omega. These are the three things which I need to find. Okay, so solution. Uh, the relationship between HD of n and h of n is nothing but h of n is equal to the desired impulse response HD of n is multiplied with the given window function w of n. So in our case, the window function w of n, he has told that I need to use rectangular window of length 5. So I have to use here the equation for rectangular window, and we have discussed the equation for rectangular window in the previous video, right? Fine. So once I get this h of n, so I can get the equation for frequency response h of omega, and again we have discussed this equation for frequency response in the previous video. Fine. It's a symmetric filter. Once we get h of n, we will get to know that it's a symmetric filter, and since the length is 5 and since this is odd, so capital N, this is actually capital N is odd, length is odd, and it's a symmetric filter. So we have equation for a frequency response for symmetric and n is equal to odd. We make use of that equation to get the frequency response h of omega. Okay. Now, so before we proceed with designing the filter, in the very first video of this course, that is module 1 and lecture 1, we discussed about frequency domain sampling, right? So there we said that if I have a non-periodic discrete time signal x of n, and if I want to take it to frequency domain, I have to take discrete time. Why? Because the signal is discrete time, and Fourier transform. Why Fourier transform? It's a non-periodic signal, so I have to take DTFT. So what is it I end up with? I end up with capital X of omega, right? Okay, and this is periodic, right? This is periodic. Fine. Similarly, if I have an impulse response h of n, which is non-periodic and discrete time, and if I take this to frequency domain by taking discrete time Fourier transform, what is it I end up with? It is capital H of omega. Okay, fine. So in our case, see, we have to put it as D, desired impulse response. Since this is ht of n, I can write this as ht of omega. Fine. So he has given the specification in frequency domain, which is HD of n. HD of n. What is our aim? I need to find HD of n. I need to find HD of n using inverse discrete time Fourier transform equation, which we shall discuss while designing the filter. Okay, fine. So given specification in frequency domain, I need to find its desired impulse response by taking inverse discrete time Fourier transform. Once I take inverse discrete Fourier transform of HD of omega, so what is this? This is actually infinite in length. Since it's a non-periodic signal, the length of this is infinite. N is varying from minus infinity to infinity. This is an infinite in length. So since this is infinite in length and I am designing an finite impulse response filter, I want to make it finite. How do I make it finite? I make it finite by multiplying this HD of n, which is infinite in length, with a window function which is finite in length, depending upon what is the order he has given. In our case it is phi. So if I multiply this window function with the order length phi with an impulse response st of n, so I end up with h of n. Okay, so basically, so this hd of n is varying from, so it's a random, let me plot it, it's a random sample just to show that it is varying from minus infinity to plus infinity. If this is 0 and this is n. Okay, so this hd of n, once I take inverse discrete time Fourier transform, I end up something like this. Okay, now since I need to make it finite, what I'll do, I'll multiply this signal. I'm multiplying this signal with a window function, and since window function is 1 everywhere depending upon what is the length, so in our case 1 2 3 4 5, 0 to 4, right? Including 0 it is 4, the length is 5. So once, if I multiply these two, this is w of n. Okay, so if I multiply these two, so from minus infinity till minus 1, everything is 0. 0 multiplied with 0 is, everything is 0, right? So after 4, up to till n is equal to infinity, it is 0. 0 multiplied with this is actually 0. So here also I get 0. Whereas 1 into this sample, I get this sample at n equal to 0. At n equal to 1, 1 into this sample, I end up with the same sample, and 1 times this is the sample, and 1 times this is this one, this. Okay, so this is 0 1 2 3 4. This is what? This is h of n. So this is the impulse response of a FIR filter. So this is the procedure which we are going to follow while designing the FIR filter using window technique. Okay, so and this W of n depends upon what type of window he has asked for. So in this example he has asked for rectangular window, so we are using rectangular window. Okay, first we shall try to plot the given frequency response HD of omega, so that we can visualize what's happening. So it's a low pass filter, right? So it's a low pass filter, so I'm trying to plot the given HD of omega. So here I'm trying to plot this function. Okay, so HD of omega is what? It is e power minus j 2 omega. So 1 times magnitude is 1 and this is the phase. Okay, 1 times e power minus j 2 omega for magnitude of omega less than pi by 4, right? So it is actually, if I write it as 0, this is 0 and this is pi and this is minus pi, fine. And it is what? It is 1 times e power minus j 2 omega. So if I consider only magnitude, so 1 times 1 for what? Magnitude of omega is less than pi by 4. When I say magnitude, okay, so I have to consider both positive side as well as negative side. So don't get confused. Usually magnitude means what? I have to consider only positive side, but in this particular case, whenever he give the specification for omega in terms of magnitude, so you have to consider both positive side as well as negative side. Okay, so what is this? For magnitude of omega less than pi by 4, so for magnitude omega less than pi by 4, so for example if this is pi by 2 and this is pi by 2, and if this is pi by 4 and this is also, this is pi by 4. Okay, so it is 1 times, it is 1, right? 1 times e power j to omega, but magnitude it is 1 for magnitude of omega. for magnitude of omega, so less than pi by 4. So I have to consider both positive side as well as negative side. So minus pi by 4 to pi by 4 it is. So minus pi by, since pi by 4 I have to consider both positive side as well as negative side. So minus pi by 4 to plus pi by 4 it is 1. Okay, so it is 1. Magnitude 1 times e power minus j 2 omega, but since I'm considering only magnitude I'll take it as 1. Okay, but this is also there. This corresponds to phase. Fine. and it is 0, right? And it is 0, for magnitude of omega in between pi by 4 to pi. Again I have to consider both positive as well as negative side. So pi by 4 to pi, so it is 0 in the positive side. Also in the negative side, pi by 4 to pi it is 0. Fine. So this is omega. Okay, so this is how ht of omega looks like. uh, so this is the positive frequency. From here it is positive frequency, and below 0 this is negative frequency. I mean, practically speaking, only positive frequency exists, negative frequency does not exist, right? So just to compensate with the formula, so we are taking both positive side as well as negative side. Fine. Now, so what is this? This is discrete time Fourier transform of HD of n, right? Now I want HD of n. So what I'll do, I take inverse dt ft. If I take inverse discrete time Fourier transform of this signal, so what is the formula? Hd of n is equal to 1 by 2 pi, integrating from, I have to consider one period, I'll take minus pi to pi. Okay, I can take even 0 to 2 pi so that I can cover one period, but so this specification exists from minus pi to pi, I'll take from minus pi to pi. Okay, so it is Hd of omega e power j omega n d omega, right? But what is Hd of omega? Hd of omega is what? Hd of omega is e power minus j 2 omega, right? From where to where? From minus pi by 4 to pi by 4, right? So let me just plug that condition here. So what do we get? Let me write it here. 1 by 2 pi, integrating from where to where? Minus pi to pi, but this exists only from minus pi by 4 to pi by 4. Minus pi by 4 to pi by 4. And what is St of n? It is 1 times e power minus j 2 omega into this term e power j omega n d omega, right? And let me write it here. So 1 by 2 pi, integrating from minus pi by 4 to pi by 4. So if I take e power j omega common, what is that I end up with? It is n e power j omega n minus 2 e power minus j 2 omega, right? D omega. Fine. So what is the integration of e power j omega n minus 2 with respect to omega? So it is nothing but 1 by 2 pi, I retain as it is. It is e power j omega into n minus 2. Let me call this as equation 1 because I need it later. Okay, I'll call this as equation 1. Okay, now let me just do the integration. So it is divided by coefficient of omega is j into n minus 2, and integration limit is minus pi by 4 to pi by 4, right? So this is equal to, let me write it here, 1 by 2 pi. I'll take this j into n minus 2 out because it is independent of omega. Now this is upper limit minus lower limit. Upper limit is what? E power j pi by 4 into n minus 2, minus lower limit is e power minus of j pi by 4 into n minus 2, right? Now what is sine theta? Sine theta is what? E power j theta minus e power minus j theta divided by 2j, right? Okay, let me apply this result here. We have e power j theta minus e power minus j theta. Fine. If I take this 2j to the left hand side, so what I get, 2j sine theta is equal to e power j theta minus e power minus j theta. But this in terms of sign I can write it as 2j times sine of pi by 4 into n minus 2, right? Let me write it here. So h d of n is equal to 1 by 2 pi into j n minus 2 into 2j times sine of what, pi by 4 into n minus 2, right? So 2j times sine of pi by 4 into n minus 2 because of this result. Okay, now 2j cancels out. I end up with hd of n is equal to sine of pi by 4 into n minus 2 divided by pi into n minus 2. Okay, this is our hd of n. What happens for n equal for n not equal to 2? Why? What happens for n equal to 2? If I substitute n equal to 2, sine of pi by 2 into 2 minus 2. Sine, this is 0, right? Sine 0, and this is also 0. 0 by 0 condition exists. Okay, so this equation is valid for all values of n except at n equal to 2. Okay, but what about for n equal to 2? So for n equal to 2, so we will make use of equation number 1. Okay, what is our equation number 1? Our equation number 1 is this, right? This is our equation number 1. So let me copy that this equation. So what do I have? Hd of n is equal to 1 by 2 pi integrating from minus pi by 4 to pi by 4 e power j omega into n minus 2 d omega. This is our equation number 1, right? But for n equal to 2, right? When I put n equal to 2 here, let me write it here. So hd of n is equal to 1 by 2 pi integrating from minus pi by 4 to pi by 4. If I put n equal to 2, what happens? This e power 0, e power 0 is 1 and 1 times d omega, right? 1 times d omega. This is what I end up. So now integration and differentiation cancels out. I end up with omega with the limit minus pi by 4 to pi by 4, right? So what happens? Therefore, hd of n is equal to 1 by 2 pi with omega, and the limit is minus pi by 4 to pi by 4. So this is equal to 1 by 2 pi, upper limit is pi by 4, minus of minus plus lower limit is also pi by 4, and this is equal to 1 by 2 pi into 2 times pi by 4. So this is pi by 2. So this is equal to pi cancels out. I end up with 1 by 4. Okay. So therefore hd of n is equal to 1 by 4 for n equal to 2. Let me write combinedly. So what is hd of n now? hd of n is what? This sine of pi by 4 into n minus 2 for n is not equal to 2 and equal to 1 by 4 for n equal to 2. Okay. So we found hd of n, desired frequency response. Now what I need to find is, I need to find the impulse response for the given specification h of n, right? How do we get h of n? We have to multiply w of n with hd of n. So we found hd of n, right? Now for that hd of n, I have to multiply with w of n. So this is easy. Why? Because w of n is 1 everywhere, right? So 1 into hd of n, I end up with h of n itself. Sorry, h of n itself, and h of n is hd of n, right? So therefore h of n is equal to what? H d of n into w of n. So where w of n is equal to 1 for n in between 0 to 4 and equal to 0 otherwise. So it's a rectangular window, right? Now 1, and this is what n is varying from where to where? 0 to 4. And so this is actually for n not equal to 2 and n equal to 2 also, and here n is what? Infinite in length, right? So n is varying from minus infinity to infinity. Okay, so here n is varying from minus infinity to infinity. Now since w of n is 1 for n varying from 0 to 4, so what I end up with? this is 1, right? This is 1 everywhere for n varying from 0 to 4. So therefore what is h of n? H of n is equal to hd of n itself, but for n varying from where to where? 0 to 4. Okay, so therefore so h of n is equal to hd of n is equal to, so what is the hd of n equation we have? Hd of n equation is this, which is equal to sine of pi by 4 into n minus 2 for n not equal to 2, right? And it is 1 by 4 for n equal to 2, and n is varying from where to where? N is varying from 0 to 4. Okay, how did I take this 0 to 4? Because it is given in the problem. I had to take n varying from 0 to 4. In the sense, it's a fifth order filter, including 0, it is total samples is 5, right? So h of 0 is equal to what? Sine of what? Pi by 4 into 0 minus 2, comma, h of 1 is equal to sine of pi by 4 into 1 minus 2, comma, h of 2 is what? H of 2 is what? For n equal to 2 it is, I cannot use this equation, okay? For n equal to 2 it is 1 by 4, right? So h of 3 is equal to sine of what? Pi by 4 into 3 minus 2, comma, h of 4 is equal to sine of pi by 4 into 4 minus 2. Okay, I did a mistake here. This is divided by pi into n minus 2, right? I'm sorry for that. Now this is divided by pi into n minus 2, right? So this is divided by pi into n minus 2, divided by pi into n minus 2. But n is 0 here, n is 1 here, and this is divided by pi into 3 minus 2, and this is divided by pi into 4 minus 2. Okay, now let me just solve this equation. You have to put your calculator in radians mode. So sine of, so pi by 4 into 0 minus 2, 0 minus 2 divided by, it is pi into, divided by pi into, pi into, so it is 0 minus 2, 0 minus 2. So I end up with 0.159. So this equation is 0.159. Okay. Similarly, for n equal to 1, let me just replace 0 by 1 here. So for n equal to 1, it is 0.225. So this value is 0.225. N equal to 2 is 1 by 4. N equal to 3, let me replace this by 3. So I end up with 0.225, 0.225, and for n equal to 4, I end up with 0.159. So this is 0.159. Okay, so if you look at it, it's a symmetric, right? First sample is equal to last sample, second sample is equal to last but one sample, and middle sample is 1 by 4, right? So therefore, so our h of n is equal to what? 0.159, comma 0.225, comma 0.25, comma 0.225, comma 0.159. So this is our h of n. Okay, so only if they ask you to get h of n, you have to stop here. But apart from this, what is that they have asked? They have asked us to find what? They have asked us to find frequency response h of omega, right? So for frequency response h of omega, since it is symmetric and n is odd, because I have to find the fifth order uh, FIR filter. So the frequency response is given by h of omega is equal to what? E power minus j omega into n minus 1 by 2 times h of n minus 1 by 2 plus summation n varying from 0 to n minus 3 by 2 into 2 times h of n into cos of omega into n minus 1 by 2. So now n is what? The length is 5, right? So if I substitute the value of 5 here, h of omega is equal to e power minus j omega into, so 5 minus 1, 4 by 2 is 2, right? To 2 omega into, so h of 4, this is 5 minus 1, 4 by 2 is h of 2 plus summation n varying from 0 to, this is 5 minus 3 is 2, 2 by 2 is 1, right? So n takes value 0 and 1, only 2 value n takes here, okay? 2 times h of n into cos of omega into, so the 5 minus 1 is 4, 4 by 2 is 2, so it is n minus 2, right? So let me just expand the summation. H of omega is e power minus j 2 omega into h of 2 plus, when n equal to 0, it is 2 times h of 0 into cos of minus, this is 0, so this becomes omega times 0 is 0, minus of omega times 2 is 2 omega. So cos of minus 2 omega is cos of omega because it's a symmetric, right? So it is cos of minus 2 omega is cos omega because it's a symmetric. So what do I end up with? Is here is cos of 2 omega, right? Plus, when n equal to 1, 2 times h of 1 into cos of minus omega, which is cos of omega. This is cos of omega, right? So h of omega is equal to e power minus j 2 omega into, what is the value of h of 2? So this is h of 0, h of 1, h of 2, h of 3, h of 4. So value of h of 2 is 0.25 plus 2 times h of 0, 2 times 0.159, which is equal to 0.318 into cos of 2 times omega, plus 2 times h of n, h of 1 is 0.225, 2 times 0.225 is 0.45 into cos of omega. So this is the magnitude frequency response h of omega which we need. Okay, so this is about designing a FIR filter, fifth order FIR filter using rectangular window. Okay, we shall try to verify our design what we did theoretically in MATLAB. Okay, the command here is, so h is an variable which I am taking. The command to get the coefficient of a FIR filter is FIR1. Okay, this is the command, and I have to pass totally 4 arguments here. First argument is order, but while giving here I have to give order minus 1. Since it's a fifth order filter, I will be giving 4. Okay, this is a format which we have to pass. Okay, order minus 1. First parameter is order minus 1. Next is the cutoff frequency, which is 1 by 4. What we had was e power, for magnitude of omega less than pi by 4, right? So pi by 4, which is in terms of pi, it is 1 by 4. So I had to give here in terms of pi. Okay, comma, the type of the filter. Since I'm designing a low pass filter in a single quote, I need to pass it as low. And the last argument is which window I am using. So I am using rectangular window, and the command for rectangular window is what? RECTWIN, off. And what is the order? It is, what is the length? Fifth order, right? So if I hit enter, so if you just check, for h of 0 is 0.159 we got theoretically, but practically it is 0.15. It's fine. 0.22, h of 1 is 0.225 we had, but here it is giving us 0.22. So this is also fine, no issues. And h of 2 is 0.25 we had, it is giving us 0.24. This is also fine, and it's symmetric. This is equal to this, and the last sample is equal to first sample. Okay, now even you can get magnitude versus frequency and phase versus frequency plot also. So the command is freq z of the coefficient which is there in h, right? So if I hit enter, this will automatically give us frequency response. So this is magnitude versus frequency, and this is phase versus frequency. So this is fine, but we are interested in this frequency plot. So and the problem he has told us to get h of omega, right? Frequency response h of omega, that is what is this. So in that equation, if you substitute values for omega like 0 times pi, 0.1 times pi, 0.2 times pi, 0.3 times pi, note down the values, and if you try to plot it, you get something like this. Okay, so this is in dB, but if you need to convert whatever the h of omega you got, you have to convert it to decibel. That will be in the ratio. So now this is in dB. Fine. So this is how we verify the designed filter in MATLAB.